Welcome back. We are still on chapter 3 semiconductors of the new textbook, and this recording we're going to do some problems on the first half of the material that we covered from chapter 3, which was an introduction to intrinsic semiconductors, doped semiconductors, and then an introduction also to drift and diffusion in doped semiconductors. So those were the topics that I discussed in the lecture, and so let's see if we can do some examples and some problems in order for you to better understand and be able to handle these numbers, because some of these numbers are different, large, small, etc. I also know that you may not have the example. Normally, if I do an example from the textbook, I am confident that you also have the textbook and you can actually see the example solved either in English or in your language, in Chinese, so that you can then spend some time on it and become more acquainted with it. Since you may not have it for this chapter, I actually hand wrote the examples also. So we may have to go to my PDF file to look up the examples also and how they are solved. Okay. All right. So with that, I am on slide 14 of the PowerPoint, where I introduce you to the first example, and this is from the textbook. It's example 3.2, and I will read there's no circuit drawing or anything, it's just a description of the problem, and then we'll look at the solution. So we are on doped semiconductors, and to just look at some of the theory, I'm actually going to go back one slide to slide 13 and pull up all the material that I had shown you regarding n-type doping and p-type doping. So on the left is n, on the right is p, and see the new terms and some of the relationships. So we say that the number of donor atoms per cc that are being provided by the dopant or the doping material, we represent that by Nd, which is the density of the donor atoms. Similarly, if the donor is a p-type or acceptor atoms, then we call it Na. After the doping has happened, the density in the n-type may have changed, and the new density of free electrons is N with a small n. Similarly, if it happens, there's maybe a new p hole density also still in the n-type, and we call that Pn. Similarly, if the doping was a acceptor type and we ended up with a p-type silicon now after the doping, that means it has more holes, then the pp will be high hole density, and the np will also be there. It may have changed, and it's shown as np. A very important formula is the one that you see in the middle, Pn. If you multiply, you get that to be Ni square. So what that means is the intrinsic density, right? With no doping, Ni is considered the intrinsic density, both for n and both for electrons and holes, right? Because we know that intrinsically, with no outside doping, no external doping, the density of the electrons equals the density of the holes, and that's represented by Ni. So even though after doping the densities of the holes and the electrons change, the product of the two still equals the square of the intrinsic density, Ni square. So Pn Nn equals Ni square on the left side. Similarly, on the right side, Pp Np also equals Ni square. And this Ni square is a constant, generally considered a constant for a given temperature for silicon, and we use it a lot in solving problems. Okay, so remember that. That equation, and then the following equation on both the left and the right. Once you know the new doping level for the majority carrier, so if it's electrons and we have n-type material that has been created because of donor atoms, then we know what the new density is for the electrons. But we still may be interested in knowing what the minority carrier density is, that is, what hole density exists. And to do that, you have to use this formula, the one on the bottom, which is Pn is Ni square by Nd on the left side, and on the right side, where the electrons are the minority carrier, then the electron density is also Ni square by Na in this case. That means the acceptor donor, the acceptor doping density. Okay, I think we'll do the next problem on the next page, and that will clear it. So let me move on. And the problem here is pretty straightforward. So we have n-type silicon. That means the dopant concentration was donors. So Nd at 10 to the power 17 per centimeter square was the impurity, was the dopant, and that was put into our silicon. So now the whole silicon bar has become n-type. So all he's saying is find the electron and hole concentrations at a temperature of T equals 300 K, which is basically room temperature. Okay. So there are two formulas to use, and actually let me open my examples PDF, and this one also I posted. It's called SNS chapter 3 examples, and I'm on page 1. Okay. So we've been given, and this is example 3.2 from the text, the donor doping is Nd equals 10 to the power 17. That's the density. Now we have to find, after the doping, we have to find both the electron density and the hole density. Remember, the whole silicon bar has become n-type now, but we just have to find the densities. Okay. So the first step is to find the electron density, Nn, and that's pretty straightforward because it just equals the density of the doping material, right? And that has already been given, so we get that. But to find the other density of the other element, which are holes, so now we want to find Pn, which is the hole density in the n-type material. We have to use this formula, Ni square by Nn, right? Because that gives you because the product of the two will always be Ni square. So to find one, you take Ni square and divide by the other density. And we know Ni is a constant. It's 1.5 into 10 to the power 10 for silicon at 300 degrees K. This is an intrinsic, this is a natural property of silicon. No doping, just the temperature is the room temperature. What is the density of silicon, of electrons in silicon? This is what you get, 1.5 into 10 to the. So use that value on the numerator in the formula below for Pn. Of course, you have to square it, and then divide by that new density, the new electron density, and the division will give you the hole density. Okay, last step, I say notice that the electron density after doping is much higher, right? That's because after doping it's 10 to the power 17. Before doping it was only 10 to the power 10. So it's 7 times, 7 magnitudes, not times, 7 magnitudes. Remember, every time you add a 1 to the numerator and when you're raising it to 10, you're actually multiplying it by 10 times. So 10 times, 10 times, 10 times, all the way to 7 is a significantly large number, right? So that is how bigger the doped n-type electron density is compared to the intrinsic or undoped. Also notice that after doping, the n-type electron density is much higher than the hole density. Before doping, they are generally considered equal, right? Electron density equals hole density. But after doping, look how small Pn is. It's only 10 to the power 3, but Nn is 10 to the power 17. So the balance has shifted very significantly. Okay? All right, so that is problem or example 3.2. So that was on doped and how to find the after doping densities. Let's move on to, well, now I have another problem from the back of the textbook. So we'll follow the same method as I did with the other textbook. There's nice problems in the back in this textbook also. So I picked problem 3.4 and let's look to see what it says. So the temperature is given, room temperature. Now what has happened is doping has happened to some silicon and the whole concentration has dropped below the intrinsic whole concentration, has dropped below the intrinsic by a factor of 10 to the power 8. So obviously some doping has happened and it has been n-type doping, donor doping, and that boosted, again just similar to the previous example, it boosted the n density, that is the electron density after doping very high, and it dropped the hole density very low after the doping. That's how he is given the problem. And how much has it dropped? It's dropped by a factor of 10 to the power 8. So he is asking, if this is the condition and this is all silicon, what was the concentration or the density of the donor material? What density was the donor material? How many electrons per cubic centimeter of the donor material, which is N capital D, what was that is what he's asking. Okay, I'm sure you know that this is sounding pretty similar to our previous example. The only reason I picked it up is because the way he is given it is the opposite of the way we solved the previous problem. So let's see if we can solve this together. Okay, so I'll open my other PDF. This one is called Class Problems. The other one I call it Class Examples. This one is Class Problems. Okay, so problem 3.4. Temperature is again 300. The Pn drops below Pi by a factor of 10 to the power 8 after doping, and find Nd. In doped silicon, again Ni equals Pi is 1.5 into 10 to the power 10. We used this previously. Remember, this is the intrinsic value, not doped, and they are equal. Now given Pn drops by 10 power 8, what that means is the new hole density equals the old hole density, intrinsic density, divided by 10 power 8, right? So now we have dropped to 1.5 times 10 square. Previously it was 1.5 times 10 to the power 10. Now it's 1.5 times 10 to the power 2. So a significant drop. Why did the drop happen? In hole density? Because electron density went up after doping, right? That's the simple reason, because they work in opposite ways. Okay, so how do we find out how much was the boost in the electron density? First you take the product and equate it to intrinsic density square. We know what, and from here we know what Pn is, the new Pn. So the new Nn is 1.5 times 10 to the power 8. So the old one went up also by the same 10 to the power 8. Not surprising. Okay, so what was the donor density, donor doping density? We know that the donor doping density equals the resulting electron density, and that's why we say the donor doping concentration or doping density is also the same, 1.5 times 10 to the power 18 electrons per centimeter square. Okay? So I hope you see how all of these is related to each other, and I hope it clarifies what we just did. Okay, I'm going to go back to my PowerPoint and we'll scroll along. So we were on slide 15 looking at this problem. Then we have some theory on the current flow. First we looked at drift. Okay, so we have an example on drift. I think I found this example somewhere else, so I don't have any PDF. I'm just going to solve it on this slide right away. So just to summarize some of the information related to drift current and how to calculate it, I moved back one slide to slide 17 just to refresh your memory. And here is everything we need to solve and find both J first. J is called current density, and then I is called, well, I is final current, right? So if you have the density, then you multiply by the square area and you get I in amps. So first step is to find J, the current density, and here is a bunch of formulas to help us find it. We talked about drift velocity, both P drift and N drift. We talk about resistivity. We were introduced to some factors called electron and home mobility. And then we also realized that a very important factor is the electric field, which is just the applied volts divided by length, because we are only considering a linear drop in our linear field, right? So this is okay for linear, I should say. Sometimes they give you non-linear, and this may or may not work during that time. But anyway, we have it for linear. So let's solve this problem. And of course, J, you can either use the resistivity to solve it like this, or you can just plug in all these individual values and also solve for J. Okay? Alright, so with that introduction, let's look at the example, see what they're asking. This is about drift velocity and mobility, not yet about actually current density. So a small concentration of minority carriers is injected into a silicon crystal bar. A voltage of 10 volts per centimeter is applied to the bar. Minority carriers are found to move 1 centimeter in 20 microseconds. So some kind of speed has been given for these minority carriers. And so we are asked to calculate the mobility of the minority carriers. Really speaking, it doesn't matter if either minority carriers or majority carriers are being injected. I think the calculations stay the same. Okay, so let's see how to solve this. Now, carrier drift velocity, or Vd, any velocity is distance moved by time, right? So that's been given that they're moving 1 centimeter in 20 microseconds. So 1 centimeter divided by 20, that gives you some kind of velocity. But we also know from the previous slide that velocity is dependent on the applied voltage, the field, and there's a constant of proportionality micro p or micro n. So given that mobility, given that velocity is that mobility factor micro times the electric field, hence you can say mobility is Vd by E, and we know Vd from another place above here, and so we come up with the mobility factor, right? And that's what is required. Calculate the mobility micro mu, I think that's mu, yeah, of the minority carriers. So mu equals 5000 centimeter square by something, okay? So I hope you saw how we used two formulas. One is this Vd calculation, velocity of drift velocity is mobility times electric field, and luckily we were also given that velocity a different way, and so we were able to combine the two and come up with this value for mu, the mobility. Okay. Next problem, also I've solved it right here, so we don't have to go looking elsewhere. This one is finally about current density. Okay. So a bar of silicon is doped with a n-type dopant, and the concentration of the dopant is Nd. It's 3 into 10 to the power 16 electrons per centimeter cube per volume, right? So that's given. The density of the dopant is given. A voltage of 1 kilovolt or 1000 volts per centimeter is applied. That's a pretty high voltage, but it's applied to the bar. Also, the electron mobility values have been given. These are actually constants for a certain temperature. So you have mu n and rho n, and the question is solve for the drift current density J. So the drift current density is generally the sum of the hole current and the electron current, Jp and Jn. And this is the formula, right? You've seen this formula before. So we need the concentrations P and N, and then we need the mobility factors mu P and mu N, and then we need Q, which is just the charge of an electron, and then we need the electric field E, which is volts by centimeter by length. Okay, so electron density N is nothing but the doping density Nd, and that's 3 into 10 to the power 6. Also, since it is a n-type silicon and nothing else has been given, we can safely assume that the hole density is very low, and hence ignore this term, the whole term, completely in the formula for J, for the current density. So basically we are reducing J to Jn, and then these four factors are still important, Q, N, micro or mu n and E, and we plug all of those in and we come up with this value of 4.8 times 10 to the power amps per centimeter square. Remember, this is density, this is not just current. Now if they had given us the area in square centimeters, then we could have multiplied the two and gotten a full amps, but this is just amps per centimeter square of silicon. Okay. Alright, so that was one problem. We got one more problem on drift, and then I think we have a problem on diffusion also. So let's look at the drift problem, and this is from the back of the chapter problem 3.8. So what is the problem? It's a drift problem. Find the current that flows in a silicon bar whose dimensions are, we are given a length and remember these are very small silicon bars like in an integrated circuit chip. The length is 10 micrometers, not meters, not centimeters, but micrometers, or 10 to the power 10 minus 6. And the surface area is 5 micrometers by 4 micrometers. So these are very small bar or crystal of silicon. Now he also gives us free electron density is 10 to the power 4 and free hole density is 10 to the power 16. So the electron, so this is actually a p-type bar, right, rather than an n-type, because the concentration of electrons is much lower than the concentration of holes. Okay, a voltage of 1 volt is applied end to end. And finally, he has given us the mobility factors for N and for P. So using all this, find the total drift current. Okay. All right. So I'm going to minimize this or try to open my problems and go to page 2 of my problems PDF. Okay. So just to make sure. Yeah, 500 is, yeah, I think there's a much higher density of holes than electrons. Length of bar is given 10 micrometers, and I immediately convert that to centimeters. So that's 10 raised to 10 power minus 4 centimeters, because we know there's 100 centimeters in each meter, right? Similarly, area of the bar 5 times 4, 20 micrometer square, or 5 times 10 to the power minus 4 times 4 times 10 to the power minus 4 when you're converting to centimeters. And you end up with 20 times 10 to the power minus 8. Now, drift current is current density J times area, right? To find the current, you find the density multiplied by area. J is this. We've seen this formula before. We already know Q, it's a constant. We've been given P and N based on the doping condition. We've been given mu P and mu N. These are actually constants. It's not exactly 1200, I think it's 1300 or something normally. But anyway, let's go with what they've given us. Even if they didn't, we could have actually solved the problem, because, just to show you again a real example, if you look at the very first slide, or slide number 6, where I showed you the table, you'll now find that all these problems are here. All the formulas are here for the drift current, for the diffusion current, and these important constants are also here. So mu P, for example, it was just given to us as 500, it's actually 480. Mu N was given as 1200, it's actually 1350. So even if he had not given it to us, we would have been able to still solve the problem. I just wanted to point that out. But it's been given, so let's use it. And so we've got mu P, mu N, we got E, which is volts per length, which is 1 volt divided by 10 into 10 to the power minus 4, because it was given as micrometers, I think. And so, we have everything we need to put into the formula for J, this formula. We have the Q, we have the P, mu P, N, mu N, and then the E, which is this value. So if you solve all this, you get 800. Take 800 multiplied by this square surface and you get 160 microamps as the current in that bar of silicon, the drift current only. Okay. All right, let me go back to my PPT and actually go back to the right slide. We just finished 3.8 on slide 20, and then I introduced you guys to diffusion last time. Diffusion, we have this profile of the concentration of the carrier, either the N or the P, and you take the derivative of that profile. If it's a linear profile or if it's an exponential profile, we take the derivative and plug that into the formula and we solve for the current density for diffusion. Of course, there's diffusion constants here, dN and dP, and they are related to each other through that mobility factor, electron and hole mobility, which we also saw previously with drift. And they actually are all tied together to something called Vt, which is a constant thermal voltage, 25.9 millivolts at room temperature. Okay, so this was a review of the theory, and then I also just managed to copy and paste the relevant section from the back of the table, so we can refer to this if necessary. This is the diffusion current formulas on the top, and you see there's a real value for dP and dN, right? I showed you that they exist, and they are 12 and 34 centimeters per second, centimeters square per second. So we may have to use these formulas, these constant values. Okay, and then the relationship between mobility and diffusivity. Okay, so let's look at the problem. Now this is an example also from the chapter, but since you don't have the chapter, I will go back to my PDF called examples, and let's see if we can find 3.4. Now 3.4, this example is on the top of page 2 of my PDF, and the PDF is examples.pdf, not classproblems.pdf. Okay, that's where you'll find it. Okay, so given that the whole concentration in a bar of silicon, actually let me go back to my, so let's read the problem together first. This curve is from your is in the textbook. It's a nice curve. It tells you it's an exponential profile, not linear, and so you expect an exponential formula, which is what we have here. So the bar of silicon has a whole concentration like this. So P of x equals an initial value P0 and an exponent raised to a minus x by something, right? This reminds us of the time constant and the inductive capacitive decay, right? Same thing, same concept. So the initial value PO is 10 to the power 16, and the time constant type thing LP is given to be 1 micrometer. So given this, find the whole current density JP at x equals 0. That means find it right here. This is x, the distance. So at x equals 0, the highest possible, find the value of Px. Now that Px is in, let's calculate and see what it comes out to be. Find the current IP if the bar has a cross-sectional area of 100 micrometer square. Okay, so the cross-section is given, you know the density, if you multiply the two you should get current in amps. Okay, so going back to seeing how the problem has been solved. the whole constant, okay, so this is the profile I've just repeated here, and we know P0 equals 10 to the power 16. We know that's the value you have to plug in at x equals 0, P0, but you still need to do the differentiation, because remember, in the formula we have this derivative term, right? So you have to differentiate, come up with the actual value, and then plug in at x equals 0. Okay. So given, or we know that the formula for the current density is, we are ignoring the n part, right? We are just focusing on the p part because there was no mention of n, so we drop that. So the equation is minus q dp times the derivative. Now you have to take the derivative of this exponential function, so that's what I've written here, and then that becomes this minus 1 by LP comes out when you differentiate, and then the same e function comes back in. This is the derivative of this, So we have an expression for Jp, the current density for the p-type element. Okay. So now if you substitute x equals 0 in this formula, you will get exactly at the entry point, right, at the top of the curve, the exponential curve. So that becomes 1.6 times 10 to the power 19 times dp is 12, it's given here. We also saw it in that other chart I showed you. dp is 12, LP is given 1 micrometer, which is 0.1 into 10 to the power minus 3 centimeters, so I put that here, times 10 to the power 16, which is the value of P0. So this. So remember, this function becomes 1, right? Because at x equals 0, the exponential is all 1. So that kind of just becomes 1 here. So the rest of the 3 items is what you see, 1, 2, 3. And if you solve that, you get this density for the current. Okay. Now, to find the actual amps, you take the density and you multiply it by the area, surface area, and you get 192 microamps as the current flowing through that silicon. Okay. All right. So that is, I think, all the problems and the examples I had up to now in the first 3 sections: intrinsic doping, external doping or intrinsic semiconductor, doped semiconductor, and current flow in semiconductor. So for these 3 sections we did a few problems, and hopefully these were helpful. I might assign 1 or 2 of these to your homework also, and in the next recording we will look at the remaining 3 sections of this chapter and also have 1 more recording on problems. Okay, so that was it. I will stop here and catch up later.